Hello dear students, this is Amrapali Patil, Assistant Professor, Department of Physics, Mahatma Phule, Arts, Commerce and Sitaramji Chaudhary, Science Mahavidyalaya, Varud. This is our second lecture and today we will discuss about the introduction to semiconductor. These are the outlines for the topic. Here we will discuss the introduction to semiconductor, charge carrier and electric conduction through semiconductors, doping, extrinsic semiconductor and energy level diagrams. Semiconductors. As definition, semiconductor is a material whose electrical properties lies between a good conductor and an insulator. Means its conductivity lies in between a good conductor and an insulator. Also, its resistivity lies in between a good conductor and an insulator. Examples of semiconductors are germanium, silicon, gallium arsenide, etc. But the most common semiconducting materials are silicon and germanium. There are two types of semiconductors. One is intrinsic semiconductor and second is extrinsic semiconductor. On the basis of energy band diagrams, the semiconductors can be defined as those materials which at room temperatures have partially filled conduction band and partially filled valence band. Partially filled valence band and the partially filled conduction band, and a narrow forbidden energy band gap. This energy band gap is of the order of 1 electron volt. At 0 degree Kelvin, means at absolute zero temperature, there are no electrons in the conduction band of the semiconductor and their valence band is completely filled. It means that at absolute zero, a piece of germanium or silicon acts like a perfect insulator. However, with increase in temperature, width of the forbidden energy band gap decreases. This width of the forbidden energy band gap decreases with temperature, so that some of the electrons are liberated into conduction band. Valence electrons jump to the conduction band. This implies that the conductivity of the semiconductors increases with temperature, or we can say that as temperature increases higher than the absolute zero temperature, the semiconductor materials act like conductors. So there are two types of semiconductors. One is intrinsic semiconductor and extrinsic semiconductor. So let us see about intrinsic semiconductor. An intrinsic semiconductor is made up of semiconductor material in its extremely pure form. An intrinsic semiconductor is made from purely semiconducting material. Naturally occurred semiconducting materials which are free from impurities are called intrinsic semiconductors. Pure germanium and pure silicons are the examples of intrinsic semiconductors. Following figure shows the atoms of germanium crystal at absolute zero. This is a crystal of germanium where all the germanium atoms are tightly bounded with their parent atoms. Germanium atom has atomic number 32. The valence shell orbit contains 4 valence electrons, which are free to make a covalent bond with other adjacent atoms. Each atom are attached or tightly bounded with the adjacent atom by the covalent bond. Hence, at absolute zero temperature, all the valence electrons in the germanium crystal are tightly bounded with the adjacent atom. Hence, there are no free electrons available for the electric conduction. So, we can say that at absolute zero temperature, pure germanium crystal, this germanium crystal acts as the pure insulator. This is very important sentence. You have to remember that at absolute zero temperature, intrinsic semiconductor act as insulator. But as temperature increases from absolute zero onwards, few valence electrons may acquire sufficient thermal energy to break the covalent bonds, and they jumped in the conduction band and became conduction electrons. So if valence electrons jump to the conduction band, the valence band should be empty. But this is contradictory statement, as we know that valence band may be either completely filled or partially filled but never be empty. This means that when valence electron moves to the conduction band, then at the same time in the valence band, the vacancy of electrons is created. There are vacancy of electrons, and this vacancy of electrons are in equal number of conduction of electrons. These vacancy of electrons is called as hole. These holes moves in the valence band. Hence, in intrinsic semiconductors, there are two charge carriers. One is free electrons, also called as conduction electrons in the conduction band. Second is hole in the valence band. Free electrons acquire the negative charge and holes are of the positive charge. So at any temperature higher than absolute zero temperature in an intrinsic semiconductor, the concentration of negative charge carrier electrons and positively charged carriers, that is holes, always same. This can be explained diagrammatically. This is a pure germanium crystal at absolute zero, where all valence electrons are tightly bounded with the adjacent atom. Hence, they treated as an insulator. Now, at room temperature or at the temperature greater than absolute zero, some of the valence electrons acquire thermal energy. These are the valence electron. Some of the valence electron acquire the thermal energy and get excited. Now, at room temperature or at the temperature greater than absolute zero, some of the valence electrons, these are the valence electrons, acquire some thermal energy, and the covalent bond breaks down and these valence electrons becomes free, and move to the conduction band, and when these valence electrons moves to the conduction band, there is a vacancy created in the valence band. These vacancies are called as hole. If there are two numbers of electrons moving towards the conduction band, then two vacancies are created in the valence band, and hence the concentration of holes and the concentrations of electrons are always same in case of intrinsic semiconductor. As shown in figure, there are 5 holes in the valence band, same as there are 5 electrons in the conduction band. So in intrinsic semiconductors, the concentrations of hole means the total number of holes are equal to the total number of electrons. From this, alternatively, intrinsic semiconductor can be defined as the material in which the number of conduction electrons is equal to the number of holes. When an electric field applied to the intrinsic semiconductors at a temperature greater than absolute zero, the conduction electrons move to anode and holes move to the cathodes. Hence, electric conduction means the electric current is generated due to the opposite movements of the holes and electrons. Both charge carriers moves in opposite direction, and hence the electric conduction takes place. So in intrinsic semiconductor, the two types of charge carriers, that is the positive charge carrier hole and the negatively charged carrier electrons, plays an important role in the conduction of electrons or electric conduction. Now we will discuss about the second type of semiconductor, that is extrinsic semiconductor. Before that, we should know the term doping. What is doping? The doping is the process of adding controlled amount of impurity atom in an intrinsic semiconductor so as to increase the conductivity is called as doping. As we know, in intrinsic semiconductor, at absolute zero temperature, the semiconductor acts as an insulator. But as temperature increases, the forbidden energy gap decreases in some amount, and some of the valence electrons acquire thermal energy and get excited, moving towards the conduction band. But only few electrons can get excited and becomes free for electric conduction. Hence, the conductivity of the intrinsic semiconductor is very less as compared to the conducting materials like copper, aluminium, silvers, etc. Hence, to increase the conductivity of intrinsic semiconductors, which is pure semiconductor, we should add some impurity atom to that intrinsic semiconductor. This process of adding of impurity atoms in intrinsic semiconductor is called as doping. The addition of impurity atom must be in controlled amount so as to get the adequate semiconducting material. It is about 1 part of 10 raised to power 7th. If there are 10 raised to power 7th atoms in an intrinsic semiconducting material, then 1 part of that 10 raised to power 7 atoms is added in terms of impurity. Semiconducting materials which is produced after doping is called as doped semiconductor or extrinsic semiconductor. So extrinsic semiconductor is the resultant product of the intrinsic semiconducting material after doping. The doping in the intrinsic semiconductor can be done by two ways, and depending upon the type of impurity atoms added in it, there are two types of extrinsic semiconductor: N type of semiconductor and P type of semiconductor. N type of semiconductor. This type of semiconductor is obtained when controlled quantity of pentavalent impurity atom like arsenic As or antimony Sb are added to pure semiconductor such as pure germanium or pure silicon. If antimony, which is a pentavalent impurity atom, added to pure germanium or silicon crystal structure, then one of the germanium atom is replaced by impurity atoms. Pentavalent impurity atom has 5 valence electrons in its outermost orbit, and germanium atom has 4 valence electron in its outermost orbit. See in this figure, antimony atom has 5 valence electrons and germanium atom has 4 valence electrons. When this antimony atom is added to germanium crystal, one of the germanium atom is replaced by the antimony atom. Then out of 5 electrons, valence electrons, only 4 valence electrons forms the covalent bond with the adjacent germanium atom, while 1 electron remains free. Hence, it can be easily excited from the valence band to the conduction band by the application of electric field or increase in its thermal energy. When this free electron acquires thermal energy or acquiring the applied voltage given by the electric field, it can be excited to the conduction band. Every pentavalent impurity atom donates 1 free electrons to the germanium crystal. So, pentavalent impurity atoms are known as donor impurity atom. In addition to the donated electrons, thermally generated electron hole pairs are also present in the N type of semiconductors. These are the electron hole pairs generated in the N type of semiconductor. Thus, in N type of semiconductors, the number of free electrons are more than the number of holes. So, in N type of semiconductors, electrons are called as majority charge carriers and holes are called as minority charge carriers. The conductivity of N type of semiconductors is mainly due to the negatively charged electron. So it is called as N type of semiconductor. N type means it is negative type of semiconductors, as the number of electrons are greater than the number of holes. This is the energy level diagram of N type of semiconductor. In this diagram, bottom level band is called as valence band, top level band is conduction band, and the difference between the valence band and the conduction band is called as energy forbidden gap. This is the energy forbidden gap denoted by Eg. In conduction band and the valence band, in between the conduction band and the valence band, there is a Fermi energy level shown as the dotted line, and also this Fermi energy level is near to the conduction band. Also there is a donor energy level Ed shown as the dotted line. This is donor energy level Ed, which shows the donor capacity, means there are donor electrons. Maximum number of donor electrons are available in the N type of semiconductors. Hence these electrons can easily jump to the conduction band. Hence this donor energy level is near to the conduction band. This EV is the energy of the valence band, energy level of valence band. This is EC is the energy level of conduction band. When the energy level of conduction band and the donor energy level are the difference is measures the forbidden energy gap. The difference gives the measurement for the forbidden energy gap. If this conduction energy level and the difference between the conduction energy level and the donor energy level is near about 0.01 electron volt. It is near about 0.01 electron volt. So very small thermal energy is required to excite the electrons to the conduction band. If this difference is less than the forbidden energy gap, this forbidden energy gap can also be decreases by acquiring the thermal energy. The number of holes in the valence band is less as compared to the number of electrons in the conduction band, as the N type of semiconductor contains the pentavalent impurity atom. The electrons can easily jump into conduction band, leaving positively charged immobile holes in the impurity atoms. By acquiring thermal energy and this difference of conduction energy level and the donor energy level is so small that the forbidden energy gap decreases and the valence electron can easily jump to the conduction band, and due to this the immobile positively charged holes in impurity atoms are left in the valence band. So this is about the introduction to semiconductors. We have discussed what is semiconductor, type of semiconductor, and brief discussion about N type of semiconductor. I hope you understand the topic. In the next lecture, we will discuss about P-type semiconductor, energy level diagrams in P-type semiconductors. So, thank you.